Welcome to the deep dive. Today, we are taking a scalpel to one of the core challenges in modern chip design. We're exploring a huge paradigm shift that affects basically every high performance chip you use.
Hmm.
Our focus is on very large scale integrated circuits, VLSI, and specifically a critical step called placement.
Yeah, and if you're building a chip, the quality of where you put every single component, I mean everything, it determines the speed, the power consumption, and, ultimately whether the chip is even manufacturable.
So, placement is really where we assign the physical locations to the thousands or now billions of circuit components.
That's right. The standard cells, the bigger IP blocks, everything inside the chip area. You can think of it like mapping out the entire infrastructure of a digital city.
And if you get that layout wrong,
If you get it wrong, the next stage, which is routing, where you actually draw all the wires, it just fails. Game over.
and placement isn't just one simple click, it's a multi stage process. First, there's global placement.
Yep. That finds the approximate sort of initial locations for all the cells. It usually allows for some overlap at first,
And then after that comes detailed placement.
and that's the refinement. It removes the overlaps, cleans things up, and assigns all the cells to their exact legal positions on the grid.
And for decades, the guiding star for this whole thing, especially global placement, well, it was really simple.
Yeah, singular. Keep the wires short.
Okay, so let's really unpack that historical objective. For a very long time, the holy grail was just minimizing total wire length.
Mm-hmm.
And this was usually estimated using a pretty simple geometric approximation, right? Something called half perimeter wire length, or HPWL.
Right. And the logic, is inescapable. For the earlier technology nodes, it worked perfectly fine. Shorter wires mean lower interconnect delay, so faster signal.
And less power consumption.
Exactly. Less capacitive load, which translates directly to reduced dynamic power and, generally a smaller chip area. It really seemed like the perfect goal. It had performance, power, and size all at once.
And on a global level, mathematically, the assumption was totally sound.
It was.
The sources confirm that the total wire length of a placement is actually equivalent to the total routing demand spread across all the global edges of the chip.
So if you minimize one, you're minimizing the other. At least you're minimizing the average routing demand across the whole circuit.
That's the logical assumption. But here is the massive critical flaw that modern chips have just completely exposed.
Well, the flaw is that global consistency doesn't guarantee local consistency. The optimization algorithm, while it's chasing that lowest possible total wire length, will aggressively cluster highly interconnected cells together
Why does it do that?
because it sees that local clustering as the most efficient way to reduce the sum of all the lengths. It's just doing what it's told.
And what's the result of that ultra efficient local clustering?
A massive traffic jam.
Mhm.
You might have minimized the average demand across the whole city, but you've accidentally created this localized hotspot, a region where the demand for routing just skyrockets way above what the local supply can handle.
So, this is the congestion paradox in action.
It is. Minimizing wire length may, and in today's advanced nodes, it will create locally congested regions. The algorithm effectively starves certain areas of routing resources to get that mathematically perfect global average.
And those starved areas become completely unroutable.
Exactly.
Let's try to visualize this. The source material gives a really stark example. So imagine two possible designs. The first one is a wire length optimized placement.
Okay.
Its total estimated wire length is, say, 100 units. Looks like a perfect score.
Right, fine paper, yeah.
But because of that aggressive clustering, one tiny boundary on the chip a bin edge, it has a routing demand of 6 tracks, but the physical supply is only 4.
That's an overflow of two.
Right. And that design is broken. The router cannot finish the job. It's useless.
Now, compare that to a congestion optimized placement. This second layout, its total wire length is noticeably worse. Let's say 115 units
So 15% worse on paper.
on paper. But, and this is the crucial part, because the components are distributed more evenly, every single bin edge has zero overflow. Demand never exceeds supply anywhere.
So that slightly longer design is the one that's actually manufacturable and routable.
Right. While the mathematically superior one is a failure, that difference between 100 and 115 units, that's the difference between a product that ships and a failed design cycle.
So clearly, wire length is the wrong driver. We have to focus on this idea of congestion itself. What does it actually look like, and why does it send the whole design process into a spiral?
Well, formally, congestion is what happens when the routing demand exceeds the routing supply in a localized area.
And how do we measure that?
To quantify it, the chip is partitioned into a global bin grid. You can think of it like a fine mesh of virtual squares laid over the chip. We then measure how many nets or wires have to cross the boundary of each little square. That's your demand.
And the supply.
The supply is the fixed physical capacity of that boundary, which is dictated by, how many metal layers you have, the spacing rules, the width of the wires. It's a hard limit.
And the key problem metric here is overflow. That's the amount by which demand goes over supply.
Right. And the total overflow is just the sum of all these localized overflows across the whole chip.
For a long time, the goal was to minimize that sum. But now we know even a low total number can hide a catastrophic failure in one spot.
And when you have that excessive local congestion, it triggers a kind of domino effect that just undermines everything.
It's devastating. The first and most critical failure is just routability failure. The router literally cannot complete the connections. The placement is officially unroutable.
And for the engineers working on this, that's not just a red flag. That's weeks, maybe months of lost time.
Oh, absolutely. And even if the design isn't completely unroutable, if it's just borderline congested, the router is forced to take these incredibly long, winding detours to get around the hotspots, which completely negates the whole point of minimizing wire length in the first place.
It does. Those detours drastically increase the final routed wire length,
Sure.
often way beyond that 15% cost we saw in our example.
And longer wires mean slower circuits. You get timing violations.
Massive performance degradation. The clock frequency you carefully planned for might suddenly be impossible to hit.
And this is where the real engineering pain must set in.
It is the painful design cycles. If routing fails, an engineer has to manually go back, tweak the placement, try to route it again and again. This loop can add so much time to market, so much cost.
And the problem is only getting worse.
Much worse. As density increases in new process nodes, the gap between the rising demand and the fixed routing supply just widens. It's becoming a catastrophic problem, especially for things with fixed routing fabrics like FPGAs. They're particularly sensitive.
So this overwhelming problem where a global optimization actually destroys local quality, it demanded a totally different way of thinking.
A new approach, yeah.
The core limitation was ignoring the distribution of resources. And that brings us to this fascinating moment where VLSI engineers had to borrow a concept from a completely different field.
They borrowed the concept of fairness.
Fairness?
The key intellectual leap was realizing the problem wasn't really resource scarcity. The total amount of routing capacity on the chip was usually enough. The problem was the unfair, uneven distribution of the routing demand.
It's like that proverb the source material brings up. We don't worry about scarcity, but about unfairness.
Exactly.
So instead of being a city planner who only optimizes for the shortest total road length, even if that sends 90% of the traffic down one tiny street,
Right, creating total gridlock.
we need a planner who ensures that resources are reasonably accessible to everyone everywhere. You have to avoid creating those localized traffic jams.
And the perfect framework for this already existed. It was in communication networks. The principle is called max-min fairness.
And that's used in network traffic management, bandwidth allocation.
All the time. In network management, max-min fairness ensures that no single data flow can increase its rate unless it forces a decrease in the rate of another flow that has an equal or smaller rate.
So what's the core goal then?
The core goal is to maximize the minimum resources allocated to each agent. It guarantees a baseline level of service for every single user on the network. No one gets completely starved.
Okay, so here's the technical nugget that defines this entire paradigm shift. When we talk about shifting the objective, we're talking about changing the actual math that defines a good layout.
That's it, exactly. It's the difference between minimizing the L1 norm and minimizing the L infinity norm.
Unpack that for us.
The traditional approach, minimizing total overflow, the sum of all the overflows, that's minimizing the L1 norm. It's trying to reduce the sum of all the errors, even if one single error is catastrophic.
But the new fairness approach, the max-min approach.
That's minimizing the worst case maximum overflow, which is the L infinity norm.
Nice.
By minimizing the L infinity norm, we stop caring about the overall sum. We are only concerned with shaving down the single highest peak on that congestion map.
And that enforces fairness.
It does. It guarantees that even the most disadvantaged region of the chip still meets a basic routable standard. We stop chasing a low average and start aggressively attacking the high peaks.
So changing the mathematical goal is one thing, but how do the engineering algorithms, the tools, actually implement this fairness objective? What are the key techniques?
They mainly attack the objective function that the tool is trying to minimize. So beyond just directly telling it to minimize the maximum congestion peak, a very effective method is weighted congestion minimization.
And what does that look like in practice?
Well, the placer runs a layout, then it analyzes the congestion map that results from it. Any of those little bin edges that show high congestion, a high demand to supply ratio, gets assigned a heavy penalty weight,
Like a tax.
a huge tax. So when the placer runs its next optimization pass, it sees the cost of routing through that congested edge as exponentially higher than routing through an empty space. It forces the optimizer to move cells out of those specific hotspots. It's a direct feedback loop that favors fairness.
So it makes the optimizer aware of its own mistakes, forcing it to backtrack from those really dense areas. What about techniques that physically push cells apart?
That leads you to cell spreading techniques. Since wire length minimization naturally creates these attractive forces between connected cells, you have to introduce powerful repulsive forces to counteract them.
So you're adding new physics to the model.
You're adding mathematical forces, yeah. They're applied during global placement, and they're calculated based on local cell density and the predicted routing demand. They act like internal pressure, preventing cell clusters from collapsing into a single hotspot
And all this ensures a more even distribution.
of components and therefore of routing demand. There are other methods too, like iterative refinement, where you just keep analyzing and slightly moving cells out of hotspots over multiple passes, or even simpler things like white space injection, where you just add empty space in trouble spots.
But the crucial takeaway here is that all these methods require engineers to accept a trade-off. You call it the placement triangle: fairness, timing, and power.
And the most immediate trade-off is between fairness and the initial wire lengths. You have to willingly accept a small, deliberate increase in the estimated total wire length.
That 115 unit instead of the 100.
Right. Because that small sacrifice guarantees better routability and, this is the key, a much shorter final routed wire length. Because you've eliminated all those miles of painful detours.
So you're trading a simple but physically inaccurate estimate for a physically accurate outcome. But what happens when you throw timing into that mix? Aggressively spreading cells apart could lengthen a wire that's on a critical timing path.
And that's where the complexity just explodes. Fairness optimization by itself is fundamentally blind to timing. It just sees dense routing demand.
It doesn't know which wires are important.
Not at all. So if the placer pushes cells apart for congestion's sake, and that happens to be on a critical path wire like a clock net, you've just introduced a timing violation that breaks the performance of the chip.
So how is that managed?
The most advanced modern placers, they use multi-objective optimization. They have to weigh both metrics at the same time. They consider the timing criticality of every single net along with its contribution to local routing demand.
So they might move a non-critical wire first.
Exactly. A net that contributes to high congestion but is not on a critical path, that gets moved first. Highly congested nets that are critical might only be allowed very marginal movement to preserve those timing constraints. It's an incredibly careful balancing act.
This shift toward fairness, while it's clearly necessary, must be a huge headache for the software tools themselves. What are the big roadblocks facing implementation right now?
The number one challenge is scaling and computational complexity. Optimizing for the maximum value, that L infinity norm, is just inherently harder and way more computationally heavy than optimizing for a simple sum.
And these algorithms have to run on chips with billions of cells.
Billions. So model efficiency is everything.
And the chip architecture itself is also making the problem harder, right? Especially with modern designs that mix component sizes.
Absolutely. The biggest challenge there is integration with mixed size placement. Modern chips, they don't just have tiny standard cells. They have these large immovable IP blocks or macros.
Things like embedded memories or specialized processors.
Right. And those macros aren't just big cells. They are giant immovable obstacles to routing. A large macro acts as a huge routing sink, and it also defines these hard boundaries that dictate the local supply of routing channels for all the little cells around it.
So it creates an unavoidable inherent unfairness gradient right around it.
It does. And the optimization has to be smart enough to place all the movable cells around these fixed blocks to compensate for the resource scarcity they create.
And finally, we're not just working on a flat 2D plane anymore. We're talking about a whole stack of copper highways.
Right. We need really sophisticated models to handle multi-layer routing. The capacity isn't uniform. Some layers are for power, some for clocks, some are denser than others. An accurate congestion model has to reflect all of that across maybe 10 or more metal layers, not just a simple 2D map.
And getting that right quickly across a billion transistor design.
That is the frontier of research right now.
So, this deep dive has really shown us why that quest for the shortest wire, while it was so mathematically satisfying, it led to physically unroutable designs in the modern era.
Mm.
The solution was this incredible intellectual leap, borrowing the principle of max min fairness from network traffic management to solve a highly specialized physical design problem. It was all about prioritizing local routability over some absolute global cost.
It's a really compelling example of how these resource allocation principles can transcend their original technical domains. The core challenge in VLSI placement, it shifted from geometry optimization to, well, resource equity.
And that brings us to our final thought for you. We just watched a concept, Maxmin Fairness, successfully jump the fence from communication network theory right into physical chip design.
A pretty big jump.
Given that cross disciplinary success, where else might the same idea, or maybe another foundational principle from a specialized field, be waiting to solve these massive optimization and resource distribution challenges? Think about supply chain logistics, where global cost minimization often ignores local warehouse strain, or even in large scale AI infrastructure, where optimizing data movement might create huge local bottlenecks. You now understand the power of prioritizing the minimum case. Where will you look for the next great borrowable principle?